All right, boom. Welcome back, Julian. We're at the final stage right now. So, chapter six. Yeah, chapter six. And chapter six is titled Motion on an Inclined Plane. And then we'll also be talking on work, energy, and power. Okay? That's chapter six, motion on an inclined plane. Very important. Now, if a particle of mass m is placed on an inclined plane, like a right angle triangle, at an angle of theta to the horizontal, then the force acting on it comprises of weight, reaction. Basically, weight and reaction. Those are the force acting on it. But if you want to get the four cardinal points of reactions, you have the force acting downward, which is mg sine theta, the force acting perpendicular to the mass, which is the reaction, the force acting downward, which is mg at an angle theta, that is also perpendicular to the reactant or to the reaction, and then the force acting in the opposite direction of the load on the inclined plane is mu r. Mu r, r stands for mg cos theta, okay? So, but if the object actually is in an inclined plane, it is important for you to know that if the acceleration is equal to 0, automatically the reaction is simply mg cos theta. Mg cos theta. If the reaction is equal to 0, the reaction, the value of r is simply mg cos theta. But if the body is sliding down the plane, it simply means that the force acting down the plane, which is mg sine theta, is greater than the reaction force, which is mu r, which is mu mg cos theta, right? So it is now accelerating. The acceleration at this point is no longer 0. And on that note, the force acting down the plane, the mu there is because it is rough and there's friction. So mu stands for the coefficient of friction. So that invariably means that your F becomes mg sine theta minus mu r, which is mu mg cos theta. Now, what if the particle eventually slides down the plane? Oh, sorry. What I'm talking about is when it is just about to slide down the rough plane. That is when you have mg sine theta minus mu mg cos theta. So what if the particle eventually slides down the plane? It simply means that the force acting down the plane is now greater than the mu r, which is the mu opposition force. So on that note, if you bring them in one direction, mg sine theta minus mg cos theta, mu mg cos theta actually will be greater than 0. And then if you take them to the other side and make mu the subject of the formula, you discover that the coefficient of friction will be greater than the ratio of sine theta cos theta, which is equal to tan theta. So tan theta is less than mu r when the body is sliding down the plane. Exam questions, you just have to remember that. Good. So that takes us to work, energy, and power. What is work? Work is simply the ability to do work. Oh, crazy. That's a crazy definition. Work is not the ability to do work, bro. Energy is the ability to do work. Work is the product of force and horizontal distance covered by the force. So force times the horizontal distance gives you what we refer to as work. If the force is being acted at an angle of theta, automatically the horizontal component becomes F cos theta times the horizontal distance, which is d. So at the end of the day, you end up having F cos theta d, or Fd cos theta as the case may be. After all, multiplication is commutative, right? Now, there are some key things you need to know under this subtopic of work. Number one, to obtain the distance covered by a particle in a given position vector, simply substitute the value of the time t in the position vector, and that will give you the distance covered. Let me just give you a particle has a position of 2t, comma, e raised to power 3t, comma, e raised to power cos 2t. Find the position. Okay? Find the position at t equals to 2. Substitute the value of t equals to 2, you get the position directly. If you are asked to obtain the velocity of that particle, differentiate the position vector given to you at a given time, if the time is required. If you're asked to calculate the acceleration of that particle, differentiate the velocity, and then you get that. So if you're given position, you're asked to calculate acceleration, you differentiate twice. If you're given position, you're asked to calculate velocity, you differentiate once. That's what we're saying. Nota bene, nota bene. The reverse of this process is integration. And integration means if you're given acceleration and you're asked to calculate velocity, you integrate. If you're asked to calculate distance, you integrate the velocity. Stuff like that. So, but take note, work is force times distance. So at times you can be given a 2-dimensional vector or even a 3-dimensional vector, and you're asked to calculate the force or to calculate the work done. So if it is a 2-dimensional vector that is in terms of x and y, it is important for you to calculate the force and the distance in the x direction, calculate the force and the distance in the y direction, and then add the two works together. That will give you the final work. If there are 3 dimensions, then what you have to do is to simply calculate the first dimension, second dimension, and add them up together. And you get that, just like that. So you have to remember, work done is equal to fx times dx plus fy times dy. If there are 3 dimensions, fx times dx plus fy times dy plus fz dot dy dz. Then add them up together, okay? So don't follow their vectorial means of solution. It can be very, very disturbing. All right. And then also take note. Another name for force is resistance. Let me just ask you to calculate the resistance. And you're wondering, what resistance are they talking about? Resistance is measured in ohms. How can they ask us to calculate for resistance when voltage is not given or current is not given? Resistance is a force, right? Take note, just remember that. Then that takes us to the last part of the chapter, which is not really the last part. Power is the second to the last. Power. So what is power? Power is simply the ability or the rate at which work is being done. The rate at which work is being done, measured in joules per second or Newton meters per second, as the case may be. So if you're asked to calculate the power of a particle in probably a 2-dimensional vector, first you have to understand that power is a product of force times velocity. Really? Yes. How? Because power is work done over time, and work done is force times distance. So distance over time gives you velocity. So force times velocity equals power. Good. So if you're asked to calculate the power of a particle in a 2-dimensional vector, maybe x and y, all you need to do is to calculate the force on the x, the velocity on the x, the force on the y, the velocity on the y, add the two together, and then you get the total power. If it's a 3-dimensional vector, you look for the force, the velocity on the x, look for the force and velocity on the y, look for the force and velocity on the z component, then add all of them together. That gives you the total power. Very, very important and key. Do not play with these facts. Then lastly, energy. Energy is simply the ability to do work. And there are literally 2 types of energy we are going to discuss in this chapter, which are potential energy and kinetic energy. Potential energy, of course, we know is the energy possessed by a body by virtue of its position or height, as the case may be. And the formula is given by mgh. And in some cases, when you have 2 dimensions like x and y, you have to calculate the dimension on the x, you have to calculate the potential energy on the x and the potential energy on the y component, then add them together, okay? Or you can have a unified formula of mg in bracket hx plus hy. That gives you the same answer. So potential energy is simply the energy possessed by a body by virtue of its height. And you can always calculate them depending on the question. If it's a 2-dimensional vector, look for the x component of the potential energy, look for the y component of the potential energy, then sum them together. Or simply put mgh if the component is not involved. Next, that takes us to kinetic energy. Kinetic energy is simply the energy possessed by a body by virtue of motion and speed. Good. And the formula for that is a half mv squared. And then, of course, if you are given kinetic energy in a 2-dimensional vector, you have to look for the kinetic energy on the vector part of x, then the kinetic energy on the y dimension, then you add both of them together. Or better still, you use the unified formula, which is a half m in bracket v of x squared plus v of y squared, right? So that takes us to kinetic energy lost. Yes, kinetic energy can be lost in a particular system. The kinetic energy before and the kinetic energy after cannot be equal, especially where there is collision. energy is lost in the process. So the kinetic energy before is always greater than the kinetic energy after. So on that note, you will end up finding the difference in kinetic energy of the first minus that of the second, not the other way around. It's not second minus first, it's first minus second, because initial kinetic energy is always greater than second kinetic energy. That is why there is a loss. If it was final kinetic energy minus initial, then there will be a gain, because you're indirectly telling us that the final is greater than the initial. So it's no longer kinetic energy loss, but kinetic energy gain. So since we're talking about kinetic energy loss, it is the kinetic energy of the initial minus the kinetic energy of the final, or you can use the unified formula, a half m in bracket v1 squared minus v2 squared, right? So what if you were requested to calculate the total energy loss in the system? Total energy loss becomes the difference between the kinetic energy and the potential energy. Let's assume you are given a two-dimensional vector, for example, two-dimensional vector, and you're expected to calculate the total kinetic energy loss. You have to first of all calculate the kinetic energy loss, the total energy loss, I mean, in the system. You have to first calculate the total kinetic energy loss, which of course we have discussed already, initial minus final. And then you also have to calculate the potential energy. As for potential energy, is always by virtue of the height, and it can be two-dimensional. At times they can even give it to you in the form of a triangle, so you will have to calculate the other part using Pythagoras theorem, stuff like that. So just know that the total kinetic and the total energy loss in the system is the difference between the kinetic energy and the potential energy. And the kinetic energy is a half m in bracket v1 squared minus v2 squared, then minus mg bracket hx plus hy. Thank you. That is the end of this particular course as a whole. We have done justice to maths 1 to 5. Finally, it has come to an end. Boom. See you when we meet again.